Hey class, we're going to be going over solubility today. It's our lecture 24, and hopefully clear up some ideas from the last lecture. I felt like in the last lecture I kept saying like we'll talk about this in the next lecture, so hopefully this can kind of like button up some of those ideas. All right. Okay, so solubility. So last lecture we talked about solutions. So basically the majority of the solutions you're going to see are just water with some kind of ionic compound in it dissolved in the water. Okay. So kind of a review from the last lecture. Go ahead and try this problem. All right, so question says, what is the concentration of positive charge in milliequivalents per liter, which is usually the units that you'll see for these problems. If you dissolve 2.2 grams of calcium chloride into 100 mils of water. Okay, I was trying to like add to the stoichiometry map, like how to do equivalents, but it's kind of a different, I mean, it's similar, but it was different enough that I felt like I couldn't think of a good way to add it into the stoichiometry map. So we're just going to have to kind of use the principles that we've learned before to do this. But if you want to think about it in terms of the stoichiometry map, you can kind of get there just by doing, usually we go from grams of A to moles of A over to moles of B, and then usually go to grams of B, but in this case we're going to be going to, sorry, not grams, equivalents of B, okay? All right, so from grams of A to moles of A, we know is the molecular weight. From moles of A to moles of B is the molar ratio. This is the one that it really depends on what ion you're doing. Kind of depends on the charge. So it's not a consistent number here, which is why I didn't put it in there. But this can still help us at least see where we're going when we do these problems. So we'll start with 2.2 grams of calcium chloride. Okay, and then we want to go over to moles of calcium chloride, moles of A. So we take the molar mass, which I'm going to pull up here. 111 grams for every 1 mole of calcium chloride. Okay. And then we need to go over to moles of B. And so in this case, we're looking at concentration of positive charge. So calcium is going to be our positive ion in the solution. So in every mole of calcium chloride, when it's dissolved, you have 1 mole of calcium 2+ ions, right? So now we're at moles of B. And then this last conversion, like I said, this will depend on the charge. So since calcium has a 2+ charge, for every 1 mole of calcium 2+ ions, we have 2 equivalents, right? An equivalent is a mole of charge. So this is 1 mole of 2+ charge. So it's really, there's 2 moles of positive charge in the calcium for every 1 mole of calcium. So that equals 2 equivalents. If this was like sodium or something with a 1+ charge, then you would say for every 1 mole of sodium, you have 1 equivalent, right? We kind of talked about that in the last lecture. Okay, 1 mole of aluminum 3+ charge would equal 3 equivalents, for example. So hopefully that kind of gives you an idea about that. Okay, so then that gives us the equivalents, right? And then all we need to do to get to the final answer is convert equivalents to milliequivalents. And then we need to divide by the total volume that we have to get to this final unit. Okay, so here is where I basically took you. Then you convert from equivalents to milliequivalents. 40 milliequivalents. And then you divide by the volume in liters, again, because that's the units that we have. And we get 400 milliequivalents per liter. Okay. All right, moving on. So today we're talking about solubility. Solubility, and we're going to go over a few definitions here at first, but it's the maximum amount of solute that dissolves in a specific amount of solvent. So you're going to see this represented in terms of grams of solute divided by grams of solvent, okay? So for example, sugar has a solubility in water of 300 grams per 100 grams of water. So sugar is the solute, okay? And then water is our solvent. Again, water is pretty much always our solvent in this class. Okay. So then you might see a question that says like, how much sugar can dissolve in 1 liter of water? The number that's reported is usually in terms of 100 grams of water. And we want to know how much sugar can dissolve in a liter of water, right? So in order to do that, because the solubility units are in terms of grams of water, we need to convert the 1 liter of water into grams of water first. So we could go 1 liter of water. All right, we know the density of water is equal to 1 gram per milliliter, okay? So we need to convert our liter to milliliter first. So 1 liter is equal to 1,000 milliliters. And then we can say 1 gram is, the density of water is 1 gram for every 1 milliliter. And then we can use, sorry, I should be labeling, this is grams of water for every 1 milliliter of water. And then using our solubility, we can put 100 grams of water on the bottom and 300 grams of sugar on top. And that will give us our answer. So liters cancel, milliliters cancel, grams cancel, and we're left with grams of sugar as our units. And that's what the question's asking, right? How much sugar can dissolve? So go ahead and pause the video and try this one out on your own. All right, so this should be very similar to what we just went through. A little simpler because it starts in terms of milliliters. So if we take, or if we look at the solubility that we're given, right? It's in terms of grams or per grams of water. So we need to convert our milliliters into grams. So again, the density for water is just 1. So 1 gram per 1 milliliter. And then, so now our milliliters can cancel, our grams can cancel, and we're left with grams of sugar for our answer, okay? So it's, you know, hopefully you can kind of connect these with other conversion factors. It's really just a conversion factor and you're throwing it in there and matching up units. But the idea here is that there is a set amount for each solute, there's a set amount that can dissolve in 100 grams of water, basically. So for example, let's talk about saturated solutions. So a solution of 100 grams of water with 300 grams of sugar dissolved. The solubility we've already talked about for sugar is 300 grams per 100 grams of water, okay? What that tells us is that if you have a cup that's full of 100 grams of water or 100 milliliters of water, the most amount of sugar that you can get to dissolve is 300 grams of sugar. Okay, that's the maximum amount of solute that can dissolve. And this is called a saturated solution. It's pretty, I think that term is pretty self-explanatory. It's the most sugar you can put in 100 grams of water, right? Any extra sugar that gets added on top of that won't be able to dissolve in the water. because once you reach your saturation point, you can't put more sugar, you can't dissolve more sugar in the water. Any extra sugar that goes into that already saturated solution won't dissolve, and it will just look like sugar in water. Okay. Normally sugar dissolves in water, and you wouldn't even see it if you had sugar water. But if you have so much sugar that it's saturated, once you start adding extra sugar, it doesn't dissolve. It just kind of sits there as a solid sugar particle in the water. Okay. So if you do see undissolved solid in a solution, that means the solution must be saturated, okay, already. Okay, unsaturated solution. So imagine we know that the solubility for sugar is 300 grams of sugar per every 100 grams of water, right? So if we only had 200 grams of sugar dissolved in 100 grams of water, that means we still have room to dissolve more sugar in the water. So this is an unsaturated solution, okay? So more solute can still dissolve in an unsaturated solution. Basically, you can continue to dissolve the solute until the saturation point. After that, it doesn't dissolve anymore, is really kind of the idea here. Okay. So if you add a solid like sugar to water and it does dissolve, then you would know that you had an unsaturated solution. If it doesn't, that's a saturated solution. That's kind of your test there. Okay, so those are just some terms that you need to know. I think that's the biggest thing to pull from these last couple slides. Okay, you'll want to also know how temperature can affect solubility. So that 300 grams per 100 gram of sugar that we initially talked about, way back. Okay, you'll see that it says at 25 degrees Celsius. Okay, so every temperature can change the solubility of a solution. Okay, so for solids, so if you're dissolving a solid in water, like sugar or salt or something like that, as temperature increases, okay, so as it increases, generally the solubility will increase as well. So if you looked at sugar, like glucose right here, as the temperature goes up, the solubility goes up. Potassium iodide is the salt. It goes up, the solubility goes up as the temperature goes up. So it's true for most solids. You do have like sodium sulfate, which actually goes down. That's the only one on this chart. In general, it goes up, and that's kind of what you need to remember. And then also remember that the opposite is true for gases. So for gases, if you raise the temperature of a liquid, then the solubility goes down, okay? So what's that? You might not usually think of gases dissolved in water, but they do, just at a very small amount. So you can see that this is grams of solute per 100 grams of water. So for example, let's take glucose at 20 degrees. Okay, that's right here. So glucose is about, at 20 degrees, we'd say it's about 80, right, grams per 100 grams of water. All right, and then if we took oxygen, which is the highest of these at 20 degrees, it's about 4 milligrams per 100 grams of water. So gases are much less soluble than solids, but there is a small amount of oxygen in water, and that's kind of, I mean, you probably like learned about fish pulling oxygen from water, right, with the gills. I don't really know how it works that much, but that wouldn't be able to happen unless there was actually oxygen in the water, right? So gases can dissolve in the water, okay? If you're a fish expert, you can comment below or something and tell us how it all works, okay? But just know the trends for those. So as temperature increases, solubility of solids goes up. As the temperature increases for gases, the solubility goes down, okay? Okay, and we're going to learn another law that has to do with pressures, uh, partial pressures. So we learned about Dalton's law, that the total pressure is the sum of all the partial pressures of each individual gas. And so kind of building on that idea, Henry's law says the solubility of a gas is proportional to the partial pressure of the gas above the liquid, which should make sense. So, like if you look at a can of soda, right, there is carbon dioxide under pressure, right? When you open the soda, you hear it kind of pop, right? So there's lots of CO2 dissolved in the soda, which is the carbonation, right? This shows a little bit better interface between the small air gap at the top of the can and the liquid, okay? It would look like this. So since the pressure is greater above, the carbon dioxide again is pressurized in this little area, it's going to force more CO2 molecules into the liquid with more carbonation. As soon as you open that can, the pressure here above the liquid goes down, right? Because now you've opened the can of soda. And as that pressure goes down, you're going to have a lot less gas particles above the liquid. And so you're going to have a lot less gas particles in the soda. And so, I mean, you probably notice when you open a can of soda, it will quickly decarbonate, I should say, right? Yeah, anyway. And then you may have also noticed that you could try this. If you put a can of soda in the fridge versus opening a can of soda that's at like room temperature or warm, the colder soda will taste more fizzy, and that has to do with what we learned in the last slide, where if the temperature increases, the solubility goes down, right? So if you have soda that's warmer, the CO2 is less soluble in that soda, and so you're going to have less fizz in your soda. If you keep your soda cold, it's going to have more fizz because the carbon dioxide is more soluble in cold soda than it is in warm soda. So if you like soda and really fizzy soda, keep it cold. That will, you probably already know that if you like soda, but that's why. Okay. Okay, so Henry's law, the concentration or solubility is represented here with C. K is just a constant, and then P is the partial pressure of whatever gas that is. So if you represent this as an equation, you can say the partial pressure of a gas is directly proportional to the solubility of whatever that gas is in the liquid. And this is kind of, looking at this example, you might say like, duh, right? But we can represent it with an equation which allows us to do calculations, which is cool. And these equations should be on your equation sheets for the exam. Okay, so higher pressure, right, as P goes up, oops, that's not a good arrow. As P goes up, you would expect C to go up, right? So your solubility increases as the pressure increases. All right. So let's see how that would look in an example. If you want, you can pause the video and try this on your own before we go over it. All right, let's do this. So we say, how much oxygen can dissolve in 100 milliliters of water if the air is 21% oxygen and the atmospheric pressure is 1 atmosphere? The Henry's law constant for oxygen is 1.3 times 10 to the negative third moles per liters atmospheres. Okay, so this equals your K, your Henry's law constant, okay? So all we need, so we know K, because it's just constant. In order to solve for, it says how much oxygen can dissolve, so solve for the solubility, we just need the partial pressure of oxygen. The total pressure, again, if, reviewing some of the equations from previous, I guess the previous exam, right? We talked about gas laws. The total pressure is going to equal the mole ratio times, or sorry, that's wrong. Okay, the partial pressure of oxygen equals the mole ratio of oxygen times the total pressure. Okay. All right. So it tells us we do 21%, which is our mole ratio here, times the total pressure is going to give us the pressure of oxygen. So if you ran out that calculation, you'd find that the pressure of oxygen is 0.21 atmospheres. Okay. All right. So we can plug this number in here. We have K, and we can solve for C, right? Okay. Here's just the PowerPoint running it through here. So again, you have K right here times P is going to give you the solubility of oxygen. So it's saying you can dissolve 2.7 times 10 to the negative 4 moles of oxygen for every 1 liter of water. So that's the concentration, and then I guess the rest of the question says how much oxygen can dissolve in 100 milliliters of water. So we solved for this, for C, we got our answer in moles per liter, but it's telling us that we actually have 100 milliliters of water, not 1 liter. So if you multiply that concentration times 100 milliliters, or 0.1 liters, right, it tells you how many moles can dissolve in 100 milliliters of water. Cool. Sounds good. Let me see here. All right, so in the last lecture, I talked about strong electrolytes versus weak electrolytes and how to know whether something's strong or weak. We've also talked about, with ionic compounds, how the phases can be either solid or aqueous, but never really defined when they are solid or when they are aqueous. So we're going to be talking about soluble and insoluble salts, or remember, salts are the same as ionic compounds. And this should clear up some of those ideas that we've, for now, just kind of been bypassing. Okay, so ionic compounds that dissolve in water, and I should say, yeah, dissolve in water, basically, dissociate in water, are soluble salts, okay? That should be a pretty simple definition, but soluble salts are also strong electrolytes. So we talked about in the last lecture how if they dissociate, right, into different ions, then they're strong electrolytes. Well, ionic compounds that dissolve in water, they dissolve in water because they split up into different ions, and so those are strong electrolytes. If they do not dissolve in water, they are insoluble salts, and they are weak electrolytes. Yeah, considered weak electrolytes, basically. Okay. So I guess here's just a few examples of insoluble salts, right? Insoluble is pretty obvious. If you look at a solution and you can see like there's some solids in there, then it would be insoluble, okay? So here are some solubility rules. If you don't like these, you could I don't know, there's tons of YouTube videos of people using like different mnemonic devices to memorize solubility rules, and all of them are fine. I don't really, well, at least all the ones I've seen so far are fine. But this is what your book shows you, and so I'm just going to use this one. But feel free, if you find another method to memorize these that you prefer, that's fine. But you do need to memorize these. So a ionic compound is soluble if the salt contains, so you look at the left column here, any of these positive cations, okay? Let's see, there's some exceptions to those that you have to memorize, which are over here. So the salt is, oh, sorry, let me rephrase this. So the easiest way to read this chart is to look at this arrow. So salts are insoluble if they contain any of these four anions, unless one of these four anions is paired with one of these cations. Okay, so what I'm saying with that is, like, if you had something like barium carbonate, okay, that would be insoluble because that contains carbonate, okay. But if you had sodium carbonate, that is soluble, right? Because these insoluble anions are only soluble with these four cations, okay? And you'll get some practice with this on the homework. So if you look at the second row, I think it's easier to start with on the left here, the anions, okay? So chloride, bromide, and iodide are almost always soluble unless they're paired with any of these three cations, okay? Sulfate is always soluble unless paired with any of these four cations. So that's kind of the way I would read this chart. Wherever the arrow is going, start on that side and move over. So if it doesn't match any of these criteria, then you can just assume that it's an insoluble salt in water, okay? Okay, so knowing whether a salt is soluble or not is going to be helpful to decide if it's a strong electrolyte or a weak electrolyte. And it's also going to help you come up with ionic equations, which we'll talk about at the end of the PowerPoint here. Okay, so when you do the equations, sometimes a insoluble salt is formed. So here's where you can really understand the aqueous versus the solid on the ionic compounds. So if you look at this example here, you can see that these three compounds are all labeled as aqueous. Aqueous, if something's labeled as aqueous, that means it's soluble in water, okay? If it's labeled as a solid and it's an ionic compound, then that means it's insoluble in water, okay? And you could check these against the rules that we looked at in the chart above, or in the last slide. But this is where you would, using the solubility rules, helps you decide whether to put aqueous or solid next to an ionic compound, okay? Let's see, yeah. So we're gonna get a little more practice with this at the end, but let's just kind of briefly talk about it right now. So net ionic equations is something that you'll have to know how to do. So basically, in order to do these, all you do is you look at the full chemical formula, okay, for double these are always with like double replacement reactions. If something is aqueous or soluble, what you really have, right, when you put it in water is all the ones that are aqueous, because they're soluble, they're going to split up into their individual ions. So here we're going to split up into all four of these different ions that come from these two compounds here. Right, so we got silver, nitrate, sodium, and chloride, all splitting up because silver nitrate and sodium chloride are soluble. The silver chloride actually is going to stay, right? It doesn't split up in water because it's a solid, which is insoluble in water. But the sodium nitrate does split up because it's an aqueous, which is soluble in water, okay? So this right here is referred to as the like complete, or sometimes maybe referred to as the full ionic equation, okay? So then what you can do is cancel out ions on the left and the right that really don't do anything in the reaction. So sodium is a positive cation on the left, and it's also a positive cation on the right. So sodium really didn't do anything in this reaction. Nitrate is an anion on the left and an anion on the right. It didn't really do anything. all we really have is silver comes together with chloride to form silver chloride. That's kind of the meat of what's going on in this reaction right here, okay? When you write it out like this, it looks like you're forming sodium nitrate, right? But if this is in water and this is soluble and it dissolves, really all you have is sodium and nitrate ions. And so the sodium and the nitrate ions really didn't do much. This is really kind of what the meat of the reaction. And that's kind of what the net ionic equation is. And anyway, we'll practice one at the end of the PowerPoint as well. All right, so go ahead and, well, before you pause the video, there's a new term here that I haven't defined, which is precipitate. Okay, so precipitate is just a solid, okay? So if the question asks if a precipitate forms, it's basically just saying, is an ionic compound forming that is a solid, right? Or insoluble, basically. Okay, so go ahead and, these are all double replacement reactions. Try and answer the question if precipitate forms in this reaction or not. Okay, so if you got stuck, if you look at this chemical reaction, if it's double replacement, we're going to get manganese sulfide, right? Plus, we're going to get sodium chloride. Okay, I'm not going to really worry about balancing this out because I'm not doing any stoichiometry or anything, so it's not that important. Okay, but if we look at our rules here, we want to decide, is manganese sulfide soluble or not? So sulfide ions are insoluble, right? Unless they're paired with any of these four cations, okay? So this is a sulfide, but it's with manganese, which isn't on this list. So that means that this would fall under the category of not being on the chart, or sorry, it is on the chart. I take that back. This is on the chart as an insoluble salt because it contains sulfide. It doesn't contain any of these positive ions. Insoluble means we're going to put a little S there, right? That's a solid. Sodium chloride is an aqueous compound, right? So if it contains chloride, it is soluble, unless it's with any of these cations, and it's not because it's with sodium, so it's going to be a soluble compound. Okay. All right. And this would be, if you wanted to practice doing the net ionic equation, this is what you should come up with, the net ionic equation. All right, so let's look at this other example. We got manganese chloride and sodium sulfate. Okay, so if we do a double replacement reaction, we're going to have our manganese that pairs up with the sulfate, and both of those have a, manganese has a 2+ charge. We know that because there's two chlorides here, and sulfate has a 2- charge, so we just put it like that. And then we have sodium with chloride again. Okay, so again, this is aqueous. We already know that one. Let's see, manganese isn't on the chart. Sulfate is on the chart. So sulfate is soluble unless it's paired with any of these four cations, which it's not. So that means this is going to be soluble as well. Since we didn't form any solids, that means that no precipitate forms, okay? And in this, since there isn't any solids that forms, there really isn't a net ionic equation. You could try and do it, but you'll see that everything just cancels out in this case. All right, go ahead and pause this one and try and do it on your own. All right, so let's work through this one. So if we look at the products that are formed in this reaction, we're going to have calcium, which is a 2+, mixed with iodine. Okay, so we're going to form calcium iodide. And we're also going to form sodium nitrate. So that should be balanced like that. Yep. The nitrate has a -1, sodium's got a +1. So we should be good there. Okay. All right, so let's see, is this one soluble or not? So Um, iodide is soluble unless it's with any of these three cations, and it's not, so that means that it's going to be aqueous. It's supposed to be AQ. Okay. Sodium nitrate, let's see. So is nitrate on here? Sorry, yeah, nitrate is on here. It is soluble. Sodium is also soluble, so this is going to be a soluble compound. Okay, cool. All right, we'll pause this one and see if you can do this one as well. All right, so predict the products. Hopefully this is becoming pretty, I don't know, repetitive at this point. So we have lead here with a 2+ charge, okay? And then it's going to be mixed with sulfate. Okay, and sulfate also has a 2- charge, so that should be good there. And then we're going to have sodium nitrate. Okay. And those, sodium has a +1 charge, nitrate has a -1 charge. Okay, so let's look at lead sulfate. All right. So we have sulfate is soluble unless it contains any of these 4 cations. And this is a lead 2+, right? We know that because nitrate is -1, and there's 2 of them. So we do have a lead 2+, and so it's not soluble if it's paired with lead 2+. That means this is going to be a solid. Sodium nitrate is soluble because both of these are on the soluble side. All right. So we do form a solid, so we have a precipitate that forms. And let's do this example, might as well. All right, so let's look at the net ionic equation, or complete ionic equation for this one. Remember, if there's a solid that forms, it means you can do a complete ionic equation. So lead nitrate is soluble, so that means we're going to have lead 2+ ion. And then we're also going to have, and this should have a AQ on it. We're also going to have the nitrate ion. Okay. All right, and then sodium. This is an aqueous compound, so it's going to dissolve. So sodium is in there, and that has a 1+ on it. Sorry, nitrate has a minus on it. And then we also have sulfate with a 2- on it. That's aqueous. Sorry, this pen isn't conducive to writing small. And then on the product side, we have lead sulfate, which is a solid. So that one I'm not going to draw separate ions for. And then we have sodium nitrate, which sodium again is an aqueous. And we also have nitrate, which is aqueous. All right, running out of space. All right. If we look at ions that are common on both the left and the right, sodium is the same on the left and the right, and nitrate is the same as well. So we should have lead plus sulfate gives us lead sulfate. Okay. So this was the complete ionic equation, which helps us figure out the net ionic equation. All right. Okay, so here's a problem I pulled off the homework. It's kind of similar to a homework problem, and I thought it was a good one to go through. So first what we want to do is write out the chemical equation, and then we will do the complete ionic equation, and then the net ionic equation. Okay, so before I write too much on this slide, I want to determine if sodium phosphate and barium nitrate are soluble or not, and then their products, right? So these two are going to combine to form sodium nitrate and barium phosphate. The video's in the way. Okay. All right, so we have sodium phosphate, barium nitrate, and then sodium nitrate and barium phosphate that we want to check. So the first one was sodium phosphate. I'm trying to remember here. So we know that phosphate is generally, again, always start on the side of the arrow, like the beginning side of the arrow is where you want to start for each of these. I chose this example because it's one that might confuse people if you use this chart. Again, I think there are some better mnemonic devices for memorizing the solubility rules, but I'm showing you how the book one works if you want to use it. Okay, so sodium phosphate is the first one we're looking at. We know that phosphate is insoluble unless it's with sodium, right? So sodium phosphate is soluble, okay? And then we had barium nitrate was the next one. So barium isn't really on here. Oh, but nitrate is, right? And nitrate is soluble. There really are no exceptions for nitrate. Okay, so nitrate should be soluble. Okay, so barium nitrate soluble. You can see barium down here, but it's saying basically it's only insoluble if it's paired with sulfate. Okay, so barium nitrate is soluble. So then we had sodium nitrate, which sodium and nitrate are both on this side. So that one is soluble. And then we also had barium phosphate. Okay. Oops. Yeah, barium phosphate. Okay, so phosphate is on here as insoluble unless it contains any of these positive ions. And barium phosphate basically would not fit this criteria. So barium phosphate is insoluble. Okay. All right, I'm going to write out this equation. So we said that sodium phosphate, oh, I didn't really need the parentheses, but well, is soluble. And barium nitrate is also soluble. Okay, and then we mix those and we form sodium nitrate, which is soluble. And then we also form, get the video out of the way here real quick, barium phosphate, okay, which is a solid, right? That was the an insoluble compound. Okay, so precipitate does form, right? We form a solid. Now, if I want to do the complete ionic equation, for every aqueous or soluble ionic compound, I'm going to split it up into the ions. So we get a sodium ion, that's aqueous. And then we get the phosphate ion, aqueous. And then we have the barium ion, which is aqueous. And then we have the nitrate ion, which is aqueous. Okay, and then on the product side, we're going to have sodium, which is aqueous. And we're going to have nitrate, which is aqueous. And then we have our solid formed, which is barium phosphate. Okay, that's a solid. Okay, so if we look at ions that are common on both the left and the right, so sodium would cancel out and nitrate would cancel out. So we would be left with the phosphate and the barium come together to give barium phosphate. Okay, so then this is our net ionic equation. And then this one here was our complete ionic equation. Cool. Okay, so hopefully that's making sense. Practice those, and if that chart is confusing you, I would recommend looking up like a mnemonic device for it. That's what I liked to do when I was taking the class, and I think it's helpful. But I also wanted to show the book way just in case, because there isn't really a YouTube video on the book way. But if you don't like it, then you can try another way. Anyway, hopefully that's helpful, and good luck with the homework. Get some practice with this, and see you next time.